In this question we are dealing with two random variables and we are given a joint probability for these. Random variables are S and R, and here are the potential outcomes for S and R, and the yellow part is the joint probability distribution. All these probabilities add up to 1, as of course as they should. The first question asks us to provide the marginal probability distributions for R and S. So we'll just need to add up all the joint probabilities in one row to get the marginal probability distribution for R. Here it is, probability that R equals 4 is 0.2% and so forth. And then we do the same for S. We can't really squeeze it underneath here, so we'll write it here. There are 4 potential outcomes for S. Probability that S takes -10 is 0.1, that it's 0, 0.2, and so forth. And again, these probabilities add up to 1. This is the marginal probability distribution for S. Now, what's the overall probability that the rate of return of the stock market, that's S, will be positive? Well, there are 2 positive outcomes, and the probabilities for these 2 outcomes that S is either equal to 10 or equal to 20% is 0.7 plus 0.7, that's 0.5 plus 0.2. Second, what's the probability that the stock market return S exceeds the return for the fixed interest investment R? So we can see the returns 10 and 20 for the stock market return. They will all be bigger than any return the random variable R can provide, and if you add up all these joint probabilities you get 0.7. For the second question we are being asked to calculate the mean and variance for each of the 2 marginal distributions which we just calculated. Let's start with S. The expected value of S, or the mean, is the sum, because it's a discrete distribution, of all probabilities for all outcomes times the outcome. So that's just plugging in a few numbers. The first outcome, that's little s, is the particular outcome. Big capital S is just the name of the random variable. So probability for -10 is 0.1, probability for 0 is 0.2, for 10 the probability is 0.5, and for 20 it's 0.2. And then we just need to do a little bit of calculations, and we get 10 as a result. So the expected value for the random variable S is 10. I've just replicated the marginal distribution again, so now the variance here, that is the sum of the probabilities of outcomes times the outcome minus the expected value squared. So first outcome -10 minus the expected value -10 squared, and that times the probability of 0.1. Then 0.2, that's the probability, times the outcome 0 minus the expected value squared. So always these -10 bits that will appear, they're always the subtraction of the expected value, or in order to calculate deviations. Then the outcome 10 minus 10, of course 0, probability is 0.5, and then 0.2 times 20 minus 10, again the expected value squared. So what have we got here? We get -20 squared is 400, so 0.1 times 400 plus 0.2 times 10 squared plus 0.5 times 0 plus 0.2 times 10 squared again. So that will be 40 plus 20 plus 0 plus 20, so that's 80. So the variance of S is 80. Let's go to random variable R, and here the outcome, potential outcomes, little r, are 4, 6, and 8. The name of the random variable is capital R, and the probabilities for these 3 different outcomes are 0.2, 0.5, and 0.3 as they were calculated before. So the expected value is just 0.2 times 4 plus 0.5 times 6 plus 0.3 times 8, and that's 6.2. What about the variance? So we could apply the same formula for the variance as before. The sum of all probabilities times r minus the expected value of r squared. Now the expected value isn't a nice round number, it's 6.2. So we have to square non-integer numbers. So let's try our alternative formula for the variance. That's the expected value of r squared minus the expected value of r, and that squared. That last bit we have already, so we will have to calculate something, and then we'll have negative 6.2, which is the expected value of r squared. The bit we are yet to calculate, that will now be in blue, is the expected value of r squared, and that is, as always, for the expectation, and for the continuous random variable, we'll just sum up all the r squareds, but pre-multiplied with the probability for the particular r. So we have 0.2 is the probability for outcome 4, that's squared. 0.5 probability for 6, that's squared, plus 0.3 times 8 squared. So that's now just a bit of calculations. That's 3.2 plus 18 plus 19.2, confirm that is correct. And so that is now the sum of these three terms, the expected value of r squared minus 6.2 squared, which is the expected value of r squared. And the outcome here is just going to be 1.96. So that's the variance of r. So let us just summarize what we found so far. We have the two random variables r and s, and we calculated expected values and variances for both of them. Let's just write down the results here. That's what we calculated so far. So what you can see here is that random variable s, or investment in shares, gives you higher expected returns, but also a higher risk, because that is how we will interpret the variance, or how you can interpret the variance. That's how much you have to fret about your outcomes. So, second sub-question, calculate the population covariance and correlation between R and S, and how would you interpret the value of correlation. So, covariance, of course you need to know how to calculate that. The covariance is the expected value of outcome r, little r, minus the expected value times outcome s minus the expected value of s. Now, as always, the expectation is going to be implemented by summing over all potential combinations of r and s times the probability for the outcome. So the probability that random variable r is little r and s is little s times that little r minus the expected value times that little s minus the expected value of s. Some funny things happening here with half lines disappearing. Now what we already know is that expected value of r and expected value of s. What we also need to use are these probabilities. These are the joint probabilities from the joint probability table. So now we're going to do this calculation in Excel. Here I replicated the joint probability table. That's just from the question, just replicated in Excel. Joint probability table. And now there are two more terms which we need. We need r, little r minus the expected value of r, and little s minus the expected value of s. Now you can see from the gray area there are 12 potential joint outcomes. So the sum in our formula will sum up over 12 terms. But of course for r we only have 3 outcomes, 4, 6 and 8. So for all the outcomes with 4, where r is equal 4, what is going to be little r minus expected value of r? So let's go back. Yeah, okay, let's shade that first in gray. So here these values we need. So if r is equal to 4, what is 4 minus the expected value of r? The expected value of r is of course 6.2, so it's 4 minus 6.2, and that is negative 2.2. Now that is true for all 4 outcomes where r is equal to 4. Then for all the outcomes where r is equal to 6, little r minus expected value of r is 6 minus 6.2, that's negative 0.2, so that's valid for all these 4 joint outcomes. And then for 8, we have the deviation from the mean is 8 minus 6.2, that's 1.8 for all the 4 outcomes where R is 8. Now we do the same for S. S negative 10 minus the expected value of negative 10, so that's negative 20 would be the deviation. That's the same for all the 3 outcomes where S is negative 10. Then S can be 0, and there 0 minus the expected value is negative 10. Then outcome can be 10 minus the expected value, which is also 10. Therefore the deviation is 0. I only need to copy this down here, and then if the outcome for R is 20, 20 minus the expected value is 20 minus 10 is 10. So for these 3 outcomes, the little r minus the expected value of R is 10. So now we have 12 possible combinations of R and S, and for each of these 12 combinations we have values for our 3 terms which we need in the covariance calculation. So what we now need to do is calculate the product of the joint probability times R minus the expected value of R times S minus the expected value of S. And we do that for all 12 possible outcomes. So we just copy that formula across and we get automatically the correct outcomes, and then we just need to sum up all these values, because we need to calculate the sum of this product. So that's easily done in Excel. It's just sum equals open parenthesis, then highlight all the cells and close. So the result here is negative 7.6. So therefore the covariance between R and S is negative 7.6. So I did that in Excel because it was 12 terms, it's quite a lot, but of course we would expect you, especially for small examples, to be able to calculate that by hand. So what about the correlation? This was the covariance. We were also asked to calculate the correlation between R and S. You should know the formula. That's the covariance between R and S divided by the square root of the product of the variance of R times the variance of S. And now we just need to plug in the values. We have the 2 variances, we have the covariances. If you plug up all the values, you will of course get something negative because the covariance is negative and the variance is positive, and therefore they're the square root of their product as well. So we'll get a negative correlation, negative 0.6069. Moving to the next question, here we have a new random variable A, which is a combination of the 2 random variables R and S. 0.5 times R plus 0.5 times S. So the expected value of A is just going to be 0.5 times the expected value of R plus 0.5 expected value of S. And if we just plug in the numbers, which we already have, we get 3.1 plus 5 is equal to 8.1. So halfway between the 2 individual expected values. What about the variance? So the variance formula, of course, you need to know is the weight 0.5 squared times the variance of R plus 0.5 squared times the variance of S plus 2 times the product of the 2 weights times the covariance of R and S. Again, we now just need to plug in all the values which we have, including the covariance of negative 7.6. And what we get is 16.69. So that's the variance of this new random variable A. It's like a portfolio between the 2 assets, a 50-50 strategy, 50% each. Now, why is that potentially better than any of the individual asset classes, the stocks or the fixed interest asset? So now we'll draw a graph where we have expected values of on the vertical axis and variances on the horizontal, and we'll place our 3 strategies R, S and A in that graph. So here's S. We have high variance but also high expected return of 10 percentage points. What about R? We have very low variance and lower expected return. So now the amazing thing is that if you mix these 2 under certain circumstances, in particular if the covariance isn't 0, we'll find that our combination here, A, isn't on the line between R and S, but In this case, the expected return is halfway in between due to the 50-50 weight, but the variance or risk is much closer to the less risky asset A. Now, that's a good thing because we don't like risk. So we shared the expected return halfway, but risk-wise we got much more of the less risky asset. That's pretty cool. It's called diversification.